Ever feel like you need to get your head around something really complex, but the thought of wading through endless jargon just makes you want to give up?
Yeah, it happens to everyone.
You're not alone. That's why we're here. Welcome to the Deep Dive, where we take on the heavy lifting so you can get to the core understanding fast.
And today we're diving deep into a paper that really shook the foundations of modern AI. Attention is all you need.
Exactly. This came out of a powerhouse collaboration. Google Brain, Google Research, University of Toronto.
Some serious players.
So the ideas inside are worth paying attention to.
Definitely. What these researchers, Ashish Vaswani and his colleagues, proposed was, well, a fundamentally new way for neural networks to process sequences of information.
Okay, so give us the headline. What was their big idea?
They introduced an architecture called the transformer. And the key thing is, for the first time, it could understand the relationships between all elements in a sequence simultaneously.
All at once.
Yeah, using this mechanism called attention. It was a pretty radical departure from how things had been done before, especially in tasks like translating languages.
Right, so when we talk about sequence transduction, we basically just mean taking one sequence of things, say English words,
Yeah.
and turning it into another sequence like the French translation.
Precisely. That's a perfect example. And for a long time, the standard tools for this were things like recurrent neural networks, RNNs, and convolutional neural networks, CNNs. You might have heard of specific RNN types like LSTM.
Oh yeah, LSTMs, GRUs, they were everywhere for a
These
while.
were the workhorses, exactly.
So what was the bottleneck with those? Why did we need something totally new?
Well, the paper really zeroed in on the fact that RNNs are inherently sequential. They process information word by word, in order.
Right.
Think of trying to understand a long paragraph, but you can only read one word at a time and mostly remember the word right before it.
Yeah, because each calculation depends on the one before it finished. So if you have a really long sentence, it just takes ages.
Yeah.
And throw more computers at it doesn't really speed up that single line, does it?
Not fundamentally, no. It's like that single-lane highway analogy. This sequential bottleneck was a real drag on training times, especially for longer sequences.
Okay.
Now, it's important to say the idea of attention wasn't completely brand new.
Right, people were using it a bit.
Yeah, but mostly a sort of an add-on, usually with those recurrent networks, not instead of them.
Gotcha. So the Transformers' big leap was saying, forget step by step. Let's just use attention to look at the whole thing at once.
That's the core idea, yeah.
Yeah.
The transformer architecture completely ditched recurrence, ditched convolutions for the main task, and relied solely on attention mechanisms to figure out how words relate to each other, even if they're far apart in the sentence.
And the immediate win from looking at everything simultaneously.
Parallelization. Massive gains there. Because it's not waiting for the previous word, you can process loads of it in parallel, which means you can train these models much faster. The paper famously claims state-of-the-art translation quality, but trained in something like 12 hours on 8 GPUs for their base model.
Wow, okay, 12 hours versus, what was it before? Days? Weeks?
Often significantly longer, yeah. It wasn't just a small step. It felt like a real jump.
Right, a fundamental shift. Okay, so how does this transformer magic actually work? What are the main bits under the hood?
It uses a pretty standard structure, actually an encoder-decoder framework.
Okay.
The encoder takes your input sequence, like the English sentence, and maps it into this rich numerical representation, a set of vectors, essentially. Then the decoder takes that representation and generates the output sequence, the French translation, one word at a time.
So the decoder part is still step by step.
The generation is, yes, it's autoregressive, meaning when it predicts the next French word, it looks at the English representation and the French words it's already generated.
Ah, okay, like predictive text on your phone, kind of? It uses what you just typed.
Exactly like that. Now, the key is how the encoder and decoder are built. They're made of stacks of identical layers. I think they use 6 layers in their base model.
Right, N6, yeah.
And inside each of these layers, that's where you find the crucial self-attention mechanisms and also some simpler feed-forward network layers.
Stacked self-attention, that sounds important.
Yeah.
Can you break down what self-attention actually means here?
Yeah, so within each encoder layer, there are 2 main parts. First, this multi-head self-attention. We'll get to the multi-head bit in a sec.
Okay.
And second, there's a pretty standard feed-forward network. It just processes the output for each word position independently.
Right.
The decoder has those 2 layers as well, but it adds a third attention mechanism in between them.
What does that one do?
That one lets the decoder pay attention to the output of the encoder. So when generating the French word, it can look back at the relevant parts of the encoded English sentence.
Okay, so multiple types of attention happening. What does the basic attention calculation,
Right.
what does it actually do?
Yeah.
Does it work
Well, at its heart, attention is a way for the model to weigh the importance of different parts of the input when processing a specific part.
like highlighting the relevant words?
Kind of, yeah. For each word, let's call it the query, the model compares it to all the other words in the sentence, the keys. This comparison gives a score of how relevant each keyword is to the query word.
Okay.
Then, based on these relevant scores, it creates a weighted average of the information associated with those words, the values. Words that scored higher contribute more to the output for the original query word.
So going back to the cat sat on the mat, when processing sat, the query, it compares sat to all the keys the cat sat on. It finds cat and mat are highly relevant.
Exactly.
So the values associated with cat and mat get higher weights when calculating the output representation for sat.
You got it. And the paper details a specific way to do this called scaled dot product attention. It uses a dot product for that comparison between query and key. Then it scales a result. We can talk about why in a moment, and then uses a function called softmax.
Softmax, right? That turns scores into probabilities that add up to 1.
Precisely. So you get these weights, these probabilities, telling you how much attention to pay to each value. And the beauty is this can all be done super efficiently with matrix math, making it great for parallel computation on GPUs.
You mentioned scaling. Why scale the dot product? What does that do?
Good question. They found that when the dimension of the keys, dk in the paper, gets large, the dot products can also get really large in magnitude.
Okay.
And large inputs into the softmax function can lead to extremely small gradients, vanishing gradients, basically.
Making it hard for the model to learn during training.
Exactly. So they scale the dot products down by dividing by the square root of that key dimension, fkkt. It just helps keep things stable during training.
Makes sense. A practical trick. They mentioned another type too, additive attention.
They did, briefly. Additive attention is another way to calculate the scores, but they noted that dot product attention was generally faster and more memory efficient in practice because it could leverage highly optimized matrix multiplication code.
Got it. So dot product is the workhorse. Now, what about multi-head attention? Why not just one big attention calculation?
Right, multi-head. So instead of doing one attention calculation using the model's full dimensional representation, say 512 dimensions, they first project the query's keys and values down into smaller dimensions using different learned linear transformations. They do this multiple times in parallel h times. I think h was 8 in the base model.
Yeah, H8, and the dimensions dk, dv were like 64.
Right, 512 divided by 8 is 64. So you have 8 sets of these smaller QKV projections. Each of these 8 sets goes through the scaled dot product attention mechanism independently and in parallel.
Okay, so 8 separate attention calculations happening at once.
Exactly. Then the results from these 8 heads are simply concatenated back together and then projected one more time to get back to the original model dimension.
Okay. So what's the advantage of doing that? Why split it up?
The intuition is that it allows the model to jointly attend to information from different representation subspaces at different positions.
Different subspaces.
Yeah, think of it like allowing different heads to focus on different kinds of relationships. Maybe one head learns to track syntactic dependencies like subject-verb agreement.
All right.
Another head might focus more on semantic similarity, like noticing synonyms. A single attention mechanism might just average all these different aspects together, potentially losing some nuance.
I see. So it's like having multiple experts looking at the sentence from slightly different angles and then combining their findings.
That's a great analogy. It gives the model a richer, more multifaceted understanding of the relationships within the sequence.
Cool. Okay, so we have multi-head self-attention in the encoder. And the decoder has that too, plus the extra attention layer looking at the encoder output.
Correct. That extra layer in the decoder works similarly, but the queries come from the decoder's previous layer, while the keys and values come from the final output of the encoder stack. That's how the decoder incorporates information from the input sentence.
Right, the standard encoder-decoder attention idea.
Yeah.
And there's one more twist in the decoder's self-attention, isn't there? Something about masking.
Yes, absolutely critical. Remember, the decoder generates the output sequence word by word autoregressively.
Uh-huh.
So when it's predicting the next word, it should only be allowed to attend to the words it has already generated in the output sequence and the positions before that. It shouldn't get to cheat by looking ahead at the words it hasn't predicted yet.
Ah, right. That would make the task trivial.
Exactly. So in the decoder self-attention layer, they apply a mask. It basically sets the attention scores for future positions to negative infinity before the softmax step.
So the model effectively can't pay any attention to subsequent words.
Precisely. This preserves the autoregressive property.
Okay, that makes sense. What about the other bits, the feed-forward networks you mentioned?
Right, after the attention sublayer in both the encoder and decoder, the output for each position goes through a simple feed-forward network.
Simple how?
It's just two linear transformations with a ReLU activation function in between. Position-wise means it's the same network applied independently to each position's representation.
Okay,
They used a larger dimension for the inner layer of this network, like 2048 compared to the model's 512 dimension. Just gives it more capacity.
got it. And we also need to get the words into the model in the first place.
Yes.
Embeddings.
Yeah, standard practice. Learn embeddings convert the input words, tokens, into vectors of the model dimension, D model 512.
Okay.
Interestingly, they shared the weight matrix between these input embedding layers and the final linear layer just before the softmax that predicts the output word.
Shared weights. Why?
It reduces the number of parameters in the model, which can help with efficiency and sometimes generalization. They also mentioned scaling the embedding weights by the square root of the model dimension, another small detail.
Okay, one last crucial piece. Positional encoding. If attention looks at everything at once, how does the model know the order of the words? Dog bites man versus man bites dog.
Excellent point. That's a fundamental issue since there's no recurrence or convolution tracking order.
So how do they fix it?
They inject information about the position directly into the input embeddings. Before the first layer, they add a positional encoding vector to each word's embedding vector.
Add it. Just simple addition.
Yep. This vector is designed so that each position in the sequence gets a unique encoding.
And how is this vector generated? Is it learned?
They actually propose using fixed sine and cosine functions of different frequencies. The formula looks a bit complex.
Key epos, 2i in coli, in cols. 2a pos, 2i plus 1. Yeah, I remember seeing that.
Right. The idea is that for any position, the combination of sine and cosine values across the dimensions creates a unique signature. And importantly, the encoding for relative positions might be easily learnable by the model.
So the model can figure out this word is 3 steps after that word by looking at these encodings.
That's the hypothesis. They also tried learning the positional embeddings directly, like word embeddings. They found it worked almost identically well in their experiments, but they speculated the sinusoidal version might generalize better if the model encountered sequences longer than any it saw during training.
Interesting trade-off. Okay, I think I'm getting a handle on the components. Encoder, decoder, multi-head attention, feed-forward layers, embeddings, positional encoding.
And residual connections and layer normalization around each sublayer too, which are important for training deep networks.
Right, standard deep learning practices. Now, stepping back, why is this whole self-attention approach considered so much better than the RNNs and CNNs it replaced? The paper made some strong arguments, right?
Absolutely. They compared them on 3 key aspects. First, computational complexity per layer.
Okay.
For a sequence length in n and representation dimension d, self-attention is roughly O-ning. RNNs are OND.
So which is better depends on N and D.
Exactly. Self-attention is actually more efficient when the sequence length n is smaller than the dimension d, which is often the case for the kinds of representations used in machine translation.
Ah, interesting. Okay, what's the second comparison point?
Sequential operations. This is about how much computation has to be done sequentially, which limits parallelization.
Right, the bottleneck we talked about.
Exactly. For self-attention, the amount of sequential computation is constant, O1. It can look at all pairs of words pretty much at once.
Okay.
RNNs are inherently sequential, so they require ON sequential operations, one step after another.
And CNNs.
CNNs, especially with things like dilated convolutions, can reduce this, maybe to something like O log n, but it's still dependent on sequence length. Self-attention's O1 is a huge win for parallel hardware like GPUs.
Massive parallelization advantage then. What's the third point?
Maximum path length for information to travel between any 2 positions in the sequence. This relates to learning long-range dependencies.
How easily can the model connect words that are far apart?
Right. In self-attention, any word can directly attend to any other word in one step. The path length is constant, O1.
Direct connection.
In an RNN, information has to travel step by step through the recurrent connections, so the path length is ON.
Much longer path for distant words.
Yeah, making it harder for the model to learn those long-range connections effectively. CNNs are somewhere in between, maybe O log n, again, depending on the setup. But self-attention's direct O1 path is theoretically much better for capturing those distant relationships.
So faster computation per layer, often, massively parallelizable, and much better at long-range dependencies. That sounds pretty compelling.
It really was. They also briefly mentioned ideas like restricted self-attention, where each position only attends to a local neighborhood, which could help if sequences get extremely long, like in character-level models.
Yeah.
And they noted that self-attention, followed by the position-wise feed-forward layer, is actually comparable in complexity to certain types of convolutional layers.
Okay. Anything else? You mentioned interpretability earlier.
Yes, that's another potential benefit. Because you have these attention weights connecting words, you can actually visualize them.
Look inside the model's head.
Sort of. You can see which words the model focused on when processing a specific word. The paper appendix had some really cool visualizations suggesting different attention heads were learning meaningful linguistic patterns.
Like syntax and semantics.
Yeah, some heads seem to focus on, say, noun-pronoun references, while others might link related verbs or concepts. It offers a potential window into what the model learned, which was much harder with RNNs.
That's fascinating. Okay, the theory sounds great. The comparisons seem solid. Did it actually deliver in practice? What were the results?
Oh yeah, it delivered. Big time. On the standard WMT 2014 English to German translation benchmark, their big transformer model set a new state-of-the-art BLU score that's a common metric for translation quality.
Better than everything before it.
Better even than previous ensemble systems that combine multiple models together, which usually gives a boost. And their single base model also beat all previous single models.
Wow. And was that just one language pair?
No, they showed similar top results on English to French as well. Again, achieving state-of-the-art, but crucially, with significantly less training, cost fewer floating point operations, less time on GPUs compared to the previous best models.
The tables in the paper really highlight that trade-off, right? Better scores, less training.
Exactly. Table 2 shows the comparison on resources. Their big model trained for about 3.5 days, which was way faster than comparable models at the time.
So, better and cheaper, computationally speaking. That's the dream. Did they play around with the model design much? See what really mattered?
Oh, they did. Table 3 shows experiments varying different parts. They confirmed that multi-head attention was definitely better than single head.
Okay.
Interestingly, making the heads too small by having too many heads actually hurt performance slightly, so there was a sweet spot. Bigger models generally did better, as expected, and using dropout regularization was important to prevent overfitting, especially on the bigger models.
Standard stuff, but good to confirm it holds. Now, did they only try translation? Or did they see if this transformer could, do other things?
That's a great question. They did test it on a completely different task, English constituency parsing.
Parsing. Like diagramming sentences, figuring out the grammar tree.
Exactly. Analyzing the syntactic structure. And surprisingly, even though the transformer wasn't specifically designed for parsing and they didn't do much task-specific tuning,
It worked well.
it achieved really strong results. It outperformed previous sequence-to-sequence models based on RNNs, especially when data was limited. It even got close to the performance of highly specialized, complex parsing systems that used explicit grammatical rules.
That's seriously impressive. It shows the architecture itself learned something quite fundamental about language structure.
Exactly. It wasn't just a translation machine, it was a powerful sequence processor that could generalize.
Okay, so let's try and wrap this up. The key takeaway seems to be this: attention is all you need. Paper introduced the transformer, a new architecture relying only on attention. No recurrence, no convolutions in the main path.
Right.
And this brought huge advantages in parallelization, training speed, handling long-range dependencies.
Leading to state-of-the-art results in machine translation.
And it showed strong potential for other sequence tasks too, like parsing. Basically, it changed the game.
It really did. It demonstrated the power of letting the model figure out all the connections directly across the whole sequence, rather than forcing it through a sequential bottleneck. A fundamental shift.
This has been, an incredibly insightful deep dive. It's amazing how one core idea, attention, could unlock so much progress. So, for you listening, think about this. The transformer changed machine understanding of language by focusing on relationships, not just sequence. Where else could that idea apply?
Hmm.
How could directly modeling relationships across entire datasets, looking at everything at once, change how we approach other complex problems? Maybe analyzing financial markets, understanding protein folding, or even, as the authors hinted, processing images, audio, video.
Yeah, the potential seems vast.
It really makes you wonder what happens when models can just see the whole picture instantly. And hey, if you want to dig even deeper, the authors actually released the code.
Yeah, it's out there on GitHub, part of the TensorTim Tensor library back then.
Definitely worth exploring if you're technically inclined.
For sure. This paper really kicked off a new era, and we're absolutely still feeling its impact across AI today.